Welcome, dear students. Now we discuss about 2022 Unit 2 Mathematical Modeling, paper DSE A2.2, semester 6, B.Sc Honors in Mathematics, University of Calcutta. Question paper 2022, this Group B Unit 1, Unit 2. Question 3A. Write a short note on Monte Carlo simulation method to find the value of pi. To find the value of pi by Monte Carlo simulation, consider a circle x square plus y square equal to 1 in the xy plane. The radius of the circle is 1 unit and center is at origin 0, 0. The area of this circle obviously is equal to pi r square, that is equal to pi into 1 square, that is pi square unit. So area under the non-negative curve y equal to root over 1 minus x square, y square equal to 1 minus x square, so y equal to root over 1 minus x square, and this is the graph in the first quadrant over x 0 less than equal to x less than equal to 1. This is the non-negative curve y equal to root over 1 minus x square, and so this is contained within the square of the side 1 units. This is the square of side 1 units. So area of the square is 1 square unit, and clearly the area under this shaded region, under this curve, this y equal to over 1 minus x square, is pi by 4. So pi by 4 into 4, so we get the area of the total area of this circle, unit circle. Now Monte Carlo area algorithm to calculate pi by 4 for this shaded region. Input values is this total number n of random points xy to be generated in the simulation such that 0 less than equal to x less than equal to 1 and 0 less than equal to y less than equal to 1. So this point xy is generated within this square, this. The output is the area. Area is the variable area equal to approximate area under the curve y equal to root over 1 minus x square over this 0 less than equal to x less than equal to 1 and 0 less than equal to y less than equal to 1. Step 1, initialize this counter variable, this equal to 0, integer variable this, and area is the float variable. For I equal to 1, 2, 3 up to n, do steps 3 to 5. Step 3, calculate the random coordinates xi, yi satisfying this 0 less than equal to xi less than equal to 1 and 0 less than equal to yi less than equal to 1. Step 4, calculate fxi, this equal to root over of 1 minus x square for the random point xi. Step 5, if yi, this random point yi, is less than this calculated value of fxi, then the increment, so then this xi, yi lies within this shaded region. So counter, increase the counter by 1, otherwise leave the counter as is. Next step 6, calculate area equal to counter by n, and this formula area equal to counter by n, actually this formula we use here this following formula: area under the curve, non-negative curve, divided by area of the rectangle, that is here square. This is approximately equal to number of points counted below the curve and total number of random points within this square, within the square. So area under this non-negative curve, so this shaded region area divided by total area of this square, approximately equal to this the number of points counted under this curve. The xy point under this curve lies under this curve, and divided by total number of points within this square of 1 units. So here area of the square is 1 square unit. So area under this curve, this by this is the counter, area counted below the curve, this is the counter, divided by total number of random points, this is n, and this area of rectangle is here square is 1 square unit. So this area, our required area, is equal to counter divided by n, and the required value of pi is equal to 4 into area. This Monte Carlo technique is probabilistic method and requires a large number of trials for small error. This is the disadvantage of this Monte Carlo technique. Next question 3b. Describe the linear congruence method to generate random numbers. Discuss the problem of cycling for such method. Linear congruence method to generate random numbers. This is a class of pseudo-random number generator. PRNG, pseudo-random number generator. Algorithms used for generating sequences of random-like numbers. Actually, this is not actually real random number, actually pseudo random number. This is the in a specific range. This method can be defined by this recurrence relation xn plus 1 equal to bracket a xn plus b modulo c n equal to 1, 2, 3, and dot 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 dot. But the sequence xn is the sequence of pseudo random numbers, and a, b, c are three integers, and c is greater than 0 is called the modulus, and a is 0 less than a less than c is the multiplier, and b is 0 less than equal to uh, b less than equal to c is the increment, and this b is this value of b is this, and x0 is the seed or starting value. This x0 is 0 less than equal to x0 less than c. The random integers xn are being generated in this interval, open closed interval 0 to c minus 1 for n equal to 1 to dot 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 dot. This algorithm choose the seed value, this x0 modulus parameter c, multiplier term a, and increment term b. Next, step 2, initialize the required number k of random numbers to generate. K is less than equal to c minus 1, and for n equal to 0 to k, do the step 4, this xn plus 1. Actually, we write here this xn plus 1 in this reconciliation within bracket xn plus 1 is this. It is equal to a into xn plus b modulo division c. Actually, this is the xn plus 1, actually the remainder when this axn plus b is divided by c, and the random numbers are xn plus 1. This is the algorithm. And cycling problem is this: the random numbers are repeating after a finite number of steps, generally after 6 steps. This is called cycling. Because we use an algorithm to generate random number, cycling cannot be avoided. But long cycles serve the purpose of general simulation. So we can choose a large C, say 2 to the power 31, and also AB accordingly to generate a large number of random numbers without cycling up to the C steps. Next question 3C. Consider the LPP maximizing Z equal to minus x1 plus 2x2 minus x3 subject to condition 3x1 plus x2 minus x3 less than equal to 10, minus x1 plus 4x2 plus x3 greater than equal to 6, x2 plus x3 less than equal to 4, x1, x2, x3 greater than equal to 0. The optimal table is given below. This determine the range of discrete changes in the component of B2 and B3 of the requirement vector so as to maintain feasibility of the current optimum solution. This is the problem. In standard form of the given LPP, we can write this maximizing Z equal to minus x1 plus 2x2 minus x3, 0x4 plus 0x5, 0x6 minus n x7. N is large positive quantity, and 3x1 plus x2 minus x3 plus x4 equal to 10. And this is the slack variables x4 because this is less than equal to type, and this is the minus x5 surplus variable because it's greater than type. So this is the 6 is slack variable because it's less than type inequality, less than type, and so to find to construct the initial basis matrix, so we add here this artificial variable x7, and then here xb, this 6 4 10. Actually, this the final table. This xb is this 6 4 10, and so and this 100. So corresponding x4, and this a4 is 100 initial basic matrix 100, and this 010 for this is the first column, and this is the uh, inverse basic matrix is second column, and this first column, second column, and this is the third column, and 001, x6 is 001. So this is the corresponding x6 is the third column of this. So correspondingly, B inverse is the B11, B21, B31, B12, and this x4, x7, and x6. So this choose here x4 and x7 second column, and s6 is the third column. Due to the initial and this matrix is this x4 corresponding x4 first column, x7 is the for this a7 is the third second column, and for a6 is the third column. So we choose here B inverse is this. This last final table is this 1 0 0 0 0 minus 1, and this for this x6 minus 1 1 4. So this is the B inverse. To find the variation in B2, let B2 becomes this B2 plus delta B2. Here B2 equal to, actually B2 is the this 6, B2 is 6, so 6 plus delta B2 is the new value of B2 after variation delta B2. So x4, x2, x5, because here this final table is x4, x2, x5, this equal to B inverse B. So B inverse is the value of this, and B is the 10, 6 plus delta B2, 4, because we change only B2, 6 plus delta B2, and 10 and 4 are unchanged. So this greater than equal to 0, because these all variables is a non-negative restriction. This gives, after multiplying this matrix into this, so 6, 4, minus 6, minus delta B2 plus 16. So, from the third element, this minus 6 minus delta B2 plus 16 greater than equal to 0. So 10 greater than delta B2. So delta B2 is less than this is less than 10, less than equal to 10. Since there is no lower bound to delta B2, so minus infinity less than delta B2 less than equal to 10. And this new B2, because minus infinity plus B2 adding B2, so we get this B2 plus delta B2 less than equal to B2 plus 10. Now B2 equal to 6, put here B2. So this B2 plus delta B2 is equal to this less than equal to 6 plus 10, that is equal to 16. So this B2 actually new B2. So the range of validity is this minus infinity less than B2 less than equal to 16. To find the variation in B3, let B3 becomes 4 plus delta B3, because B3 equal to 4. So this x4, x2, x5 equal to B inverse B. This B inverse already given this, and this B is the 10, 6, and B3, this new B3 is this 4 plus delta B3 is greater than equal to 0 for non-negativity restrictions of this x4, x2, x5. And after simplifying, we get this into this, multiply this into this, we get this. So obviously 10 minus 4 minus delta B3 is greater than equal to 0, and this 10 plus 4 delta B3 is greater than equal to 0. So 6 is greater than equal to delta B3, and 4 delta B3 is greater than equal to minus 10. So delta B3 is less than equal to 6, and from this inequality, delta B3 is greater than equal to minus 5 by 2. So delta B3 is the minus 5 by 2 less than equal to delta B3 less than equal to 6. Adding B3 on these sides is B3 minus 5 by 2 less than equal to B3. B3 is positive quantity. So this delta B3 is, so 4 minus 5 by 2, because B3 equal to 4. So this B3, new B3 is this. So we get the validity, range of validity is this 3 by 2 less than equal to B3 less than equal to 10. So this is the required range of validity. And extra here to find the variation in B1, and similarly we can find this for this is the 4 less than equal to B1 less than infinity. This is the validity range is of the B1. Next question, D. A small harbor has unloading facility for ships. Only one ship can be unloaded at any one time. Ships arrives for unloading of cargo at the harbor. Time span between the arrival of successive ships and unloading time of the 5 ships are given in the table below. Find the average time spent by the ships in the harbor, and total idle time of the harbor is this. Find the average time spent by the ships in the harbor and total idle time of the harbor. We have to find this. And this is the problem. We summarize this problem in this schematic diagram. This first ship initial time minute in minute 0. This after 20 minutes, ship 1 came into the harbor, enters the harbor this at this point at this 20 minute, and this unloading time is 75. So 20 plus 75 is 95, and so at this at the minute 95 minutes, this unloading is completes for ship 1. Now ship 2 enters in the harbor after 40 minutes. So 20 plus 40 is 60. So at 60 minutes, this second ship enters in the harbor. So this is the ideal time for this ship 2, because this up to 60 to 95, that is 35 minutes, is the ideal time for ship 2. And after 95 minutes, unloading for ship 2, and unloading time is 60. So 95 plus 60, that is 155 minutes, is the unloading completes for ship 2. Now, ship 3 enters after ship 2, 30 minutes after ship 2. So this 60 plus 30 is 90. So at 90 minutes, this ship 3 enters the harbor at the point at the time 90 minutes. Third ship enters in the harbor, and this is the up to 155 minutes, that is 65 minutes is idle time for uh, C3, and after 155 minutes, this unloading started for C3, and C3 unloading time is 40. So 155 plus 40, that is 195. So this is the unloading for this C3, and ship 4 enters in the harbor after 90 minutes. Uh, After 90 minutes, ship 3. So 90, this is the 90 plus 90 is actually this 180. So at 1 minute 80 minutes, this ship 4 enters in the harbor. But this up to 195, actually this 15 minutes, and this is idle time for ship 4. After 195 minutes, this unloading starts for the ship 4, and this unloading time is 50. So 195 plus 50, that is 245. Up to this 245 minutes, um, unloading um, completes for ship 4, and ship 5 enters the harbor after after 40 minutes of ship 4. So this is the 180 plus 40, that is 220 minutes. At the point 220 minutes, ship 5 enters in the harbor, and this is the idle time up to this 25 minutes. This 220 245 minus 220 idle time for ship 5, and after 245 minutes plus 70, 245 plus 70, 315 minutes, this is the unloading completes for C5. So is summary table for this random time between the sea arrival 20, 40, 30, 90, 40. This is given in the first row, and the time arrival time is 20, 60, 90, 180, 220, because first ship arrives at the point at the minute 20 minutes, and second ship enters the harbor at 60 minutes, third ship at 90 minutes, fourth ship at 180 minutes, and fifth ship at 220 minutes. And start servicing for ship 1 this 20 minutes, at the point at 20 minutes, and and servicing time at the point 95 minutes. uh, this unloading starts for ship 2, and for ship 3 at the point 155 minutes, unloading starts for ship 3, and at the point 195 minutes, unloading starts for ship 4, and at the point 245 minutes, unloading starts for ship 5 and Q length at the arrival. Here arrival at no Q, but when ship 2 enters in this harbor, so 1 Q, so wait for 1 Q, previous ship 1, and when ship 3 enters in the harbor, and the previous two ships waiting, ship ship 1, when ship 3 enters, ship 1 already starting unloading, but ship 2 is idle time. So 2, when for ship 3, 2 ships in queue, previous ships, and for ship 3 only 1 ship in queue, and for fifth ship there is only 1 ship in queue. And waiting time for ship 1, there is no waiting time, so this 0, and for ship 3 35 minutes, and for ship 3 65 minutes, ship 2 is 35 minutes, ship 3 65 minutes, and for ship 4 15 minutes, and for ship 5 25 minutes. Total waiting time is 140, and so average 140 divided by 5 is 28 is the average waiting time, and the random unloading time is 75 unloading time. Actually, the second row of this given uh, given table, this is the random unloading time for C1 75, C2 60 minutes, 40 minutes, 50 minutes, and 70 minutes. And this is the second row of the given table. And the time in harbor actually is the 75 minutes. And for ship 2, this total time in harbor actually this is the 60 minutes plus 35 minutes, actually 95 minutes. This 35 minutes plus these 60 minutes. And for ship 3, and this in the harbor, total time in the harbor is 65 waiting time, and this is the unloading time is the unloading time is 40, so 65 plus 40 is equal to 105, and this the for ship 4 is the waiting time is 15 minutes, and the unloading time is 50, so the total time in the harbor is 65 minutes, and this for ship 4, ship 5, the total time in harbor is this, idle time is 25, and unloading time is 70 plus 25, actually total time in harbor for ship 5 is 95 minutes. So total time all ships in the harbor is 435 minutes. So average time in of the ship, each ship is this 435 by divided by 87 minutes, and the dock idle time is this. Actually, this the initial time is the dock idle time. Is no ships in this initial time up to 20 minutes. Next question: this find the average time spent by the ships in the harbor. So average time spent by the harbor is 87 minutes, and total idle time of the harbor actually is the initial time is up to 20 minutes is the idle time for the harbor, and total waiting time is the 140. So average waiting time for the ships is 28 minutes, and total unloading time is 295. So average unloading for the ships 59 minutes. Next question. Question E. Consider the LPP Z-max equal to 2x plus 3y subject to condition 2x plus 7y greater than equal to 22x plus y greater than equal to 6, 5x plus y greater than equal to 10. Solve it by graphical method. Justify in this regard that any objective function of the form Lx minus my, both L, M of same sign, has finite maximum, infinite minimum subject to the constant to the above LPP. This is the you must use the graph paper in the examination, and first to convert the all inequalities to equations and draw the corresponding graphs. This so for first equation, this is the line for first equation. This is the line first equation. For second straight line, this is the second straight line is this, and for the third straight line is this, and this all inequality greater than type. So this is the convex region, is the shaded region is this, and here the objective function is this z max equal to 2x plus 3. So set this arbitrary value 18. So for objective value, value object is this. So 2x plus 3 equal to 18. So x by 9 plus y by 6 equal to 1. So this is the uh, profit line. This is the dotted line. This x by 9 plus y by 6 equal to 1 is the profit line. So this profit line, dotted line PQ, is the profit line. We move the line PQ parallel to itself away from the origin because of is the maximizing problem. So, but we cannot find any finite maximum value of z within the visible region, set region. So this LPP has unbounded solution, and this next question: if this objective function is Lx plus Lx minus my, Lm of same sign. So if objective function is suppose is z max equal to 2x minus 3y, L and M, these 2 and 3 is the are of opposite sign. L and M are of L and M are of same sign. L and M are of same sign. So here L and M are of same sign because 2 and 3 are both positive. So we write here this is not opposite, this is same sign. Same sign. This, and consider 2x plus minus 3y equal to 18. So x by 9 minus y by 6 equal to 1. And so we get this 18. This is the profit line is this. And this is the increasing direction of z is this direction. And decreasing this profit line z is equal to 12. If we put here 2x minus 3y equal to 12, this is the profit line is this. And if we put 2x minus 3y equal to minus 12, so this is the profit line. So this is the decreasing direction of this profit, and this is the increasing direction of this profit line. We cannot find any maximum nor any minimum in this case for the objective function. So this result is not true for this. Now we can describe this theorem. If the feasible region of an LPP is a non-empty and bounded convex set, the objective function must attain both a maximum and a minimum value occurring at extreme points of the region. If the feasible region is unbounded, the objective function need not assume its optimum values. If either a maximum or a minimum does exist, it must occur at one of the extreme points. Next question. Solve the following LPP by algebraic method, maximizing z equal to 10x plus y plus 2z subject to condition x plus y minus 2z less than equal to 10, 4x plus y plus z less than equal to 20 with x, y, z greater than equal to 0. This standardized form, this maximize z equal to 10x plus y plus 2z plus 0s1 plus 0s2 is the s1 is the slack variable, it's less than type, and secondly inequality is also less than type, so plus s2 is the slack variables. So x, y, z, s1, s2 are all non-negative. This here x, y, z three variables, so n equal to 3 and n equal to number of constant here 2. So number of basic solutions is equal to m plus n cm. So m plus n is 5c2. So we get 10 number of basic solutions. A solution obtained by setting any three variables among these five variables is x, y, z, s1, s2 equal to 0. Non-basic variables equals to 0. This any three variables set this non-basic variable 0, and solving the remaining m, that is two variables, is called a basic solution. This note that this algebraic method is also known as an analytical method or trial and error method. So the serial number, basic variables x, y, non-basic variables equals to 0, z, s1, s2, and put z equal to 0, s1 equal to 0, s2 equal to 0 in this equation. And after solving, we get x equal to 10 by 3, y equal to 20 by 3. So put here x equal to 10 by 3, y equal to 10 by 3 in the objective function. We get the value is 40, and the required solution is 10 by 3, 20 by 3, 0, 0, 0. Is the feasible solution? Yes, it is feasible solution. Second case, xz basic variables, y, s1, s2 non-basic variables. Sets these non-basic variables to 0 in these equations. These So after solving, we get x equal to 50 by 9 and z equal to minus 20 by 9, and this z is negative variable, so actually this is the non-feasible solution, so not feasible solution this, so we avoid this. We are only interested for the feasible solution in the first quadrant. Next, set basic variables x s1 and non-basic variables y z s2. Set non-basic variables y z s2 equal to 0. We get this, solving this, x equal to 5, s1 equal to 5. Put x equal to 5 in the objective function, so we get 50 is the value of the maximizing z is 50, and this solution is feasible solution. This 5, x1 5, x 5, y 0, z 0, s1 5 and s2 0, and this also this is non-degenerate because the non-basic basic variables are not equal to 0, so this is also non-degenerate solution. And so this we get 10 different cases, and from this table we see that this 50 is the maximized value, so we get this required solution for 50. We get x equal to 5 and y equal to 0, z equal to 0 is the required optimal solution for this problem. Next question G. A self-service store employs one cashier at its counter. An average of 9 customers arrives every 5 minutes, while the cashier can serve 10 customers in 5 minutes. Assuming Poisson distribution for arrival rate and exponential distribution for service rate, find average number of customers in the queue and average time of a customer has to spend in the queue. According to the given problem, the arrival and service of a customer both are Markovian, and the service channel is single, the capacity of the system is infinite, and the service type is first come, first served basis. So this queuing model is this MM1 infinity FCFS type model. Here, 9 customers arrive in 5 minutes. This average is, so average arrival time is lambda equal to 9 by 5 customer per minute. The average service rate mu equal to 10 by 5, that is 2 customer per minute. So rho equal to lambda by mu, this equal to 9 by 10. So average number of customers in the system is given by LS is equal to rho by 1 minus rho, which is equal to 9. And average number of customers in the queue is given by LQ equal to LS minus rho, which is equal to approximately equal to 8. Average time the customer has to spend in queue is given by WQ equal to LQ by lambda, is equal to 9 by 2 minutes. Next question. Question H. Given an arrival rate 20 per hour, is it better to get a service in single channel with mean service rate 22 customers, or at one of the 2 parallel channels with mean service rate of 11 customers for each of the 2 channels, assuming for both queues MMS infinity FIFO model? Here, MMS infinity FIFO model stands for arrival distribution is Markovian, and service distribution or departure distribution also Markovian Poisson distribution. So this MM and S for service channel is the here the multiple server. So S, and this capacity of the service is infinity. So put here infinity, and this type of service is first in first out, FIFO, or first come first service, FCFS. Now case 1, when this single channel. So this model is MM1 infinity FIFO single channel. Here the mean arrival rate lambda is the 1 by 3 customer because this 20 per hour. So by minutes divided by 60 minutes. So 1 by 3 customer per minutes, and mean service rate is 22 per hour. So 22 by 60, 11 by 30 customer per minute. And utilization ratio or traffic intensity rho is the lambda by mu is equal to 10 by 11. Expected queue length is LQ is equal to rho square by 1 minus rho 100 by 11. And expected waiting time for a customer of the queue is WQ equal to LQ by lambda. This is approximately 27.27 minutes. Case 2. When there are two channels, so MMC infinity FIFO, here C, there are two channels. Here the mean arrival rate say lambda dash equal to 20 by 60, 1 by 3 customer per minute. Mean service rate mu dash 11 by 60 because we divide this 22 up to 11. So 11 customer for each of these two channels. So put here 11. So for the second case, mu dash equal to 11 by 60 customer per minute, and utilization ratio rho dash, this lambda dash by C into mu dash is equal to 10 by 11. And so the probability having no customer in the system at the steady state, this is the P0, this formula 1 by summation n equal to 0 to C minus 1, C rho dash whole to the power n by n factorial plus C rho dash whole to the power C divided by 1 minus rho dash into C factorial. After simplifying 1 by 21, the expected queue length, that is the average number of customers waiting in the queue, this LQ dash, say this is the rho dash into C rho dash whole to the power C divided by C factorial into 1 minus rho dash whole square into P0. We get this equal to 2000 by 231, and the average waiting time of a customer in queue is WQ dash is equal to LQ dash by lambda dash, and this we get 25.97 minutes. And from 1 and 2, this WQ is expecting waiting time for a customer is 27.27 minutes, and for this second case, this waiting time is WQ dash is the 25.97 minutes. So dividing this WQ by WQ dash, this is greater than 1. So here's the WQ is greater than WQ dash. So for the first case, is the waiting time is greater than the second case. So we have the least waiting time for two service channel. Hence, it is better for a customer. For two service channel is better for a customer. Thank you for watching this video.